EECS 281, lecture number 9, Ordered and Sorted Ranges, Spring 2020. Working with containers, we know that we use them to store a variable number of other things, sometimes objects, sometimes built-in data values. They give us control and protection of our data. We can put it in a particular container that only allows limited access. They give us the ability to do some aggregate operations like copy and edit them. We can sort them. The examples, of course, that we've used already are arrays from the C style. We have kind of avoided C++ STL arrays, but we've talked about lists and maps, of course, stacks, vectors, decks, queues. These are all just containers. Today we're going to talk about how containers sort of keep things in order. So we've got a couple of examples here. On the left is this really strange game that happens here in America. It's called bobbing for apples. So what you see is a big bucket full of water, and floating in the water are some apples. And the goal is to pick up an apple with your teeth. You pick this thing up and without using your hands, but it's difficult because they're just floating on water. There's not a lot to push back. And so during bobbing for apples, you can see that if you bump one apple, it might change 2 other apples or 3 other apples near it around it. And so we think of this as an unordered container because the apples were all put in there and there's no real way to determine which apple is going to be in which place at any given time. Now, obviously, they're not jumping around by themselves, but as the container is interacted with, working on one object may change another object's relationship to even other objects. So that's what an unordered container is. In the middle, we've got an ordered container, and this is just a pea pod, and you can see that there are some peas in this pod, and they're kind of always going to be there. And you can see that the one on the end is always going to be on the one on the end, and the one next to that, and so on. So in an ordered container, things remain the same. So if I pull one of these peas out of the pod, all of the other peas stay in the exact same relationship to the remaining peas. And that's what we think of in an ordered container. On the right, we just got comedy, right? That's just a container within a container. Types of containers we're looking at. We're going to be looking at sort of their base type. So when I say type, I don't even mean ADT. I'm just talking about sort of a high-level discussion of these things. All right, so we start out with just a container. All of our containers have to support some sort of add and remove operations just to be able to put things in there and take things out. There's some other things that aren't going to be mentioned in this list of interfaces, but these are the absolute minimum set of things that I need. In a searchable container, this is like a regular container in that you can add things and remove things, but you can also add find type operations to go look for an object. A sequential container allows us to iterate over the elements in some order, and this is meaning to be a fixed order. So as I look through them, I can go from one object to the next, to the next, to the next, sequentially. After that, we have what are called ordered containers, and ordered containers are sequential containers in that I can go from one item to the next, but an ordered container will maintain its current order. You can stick something in here and expect to come back and find it here. You can remove something over there, and the items that were around the place that you removed just sort of close in around it. So you can think of books on a shelf. Books on a shelf are an ordered container because as I look at the books on my shelf, I can see if I want to pull a book out, the book to the left of it was always to the left of the books to the right of it. And even after I remove the book, it's still, those books are same in that same order. So it's not that they have to be in a sorted range. You can see books on a shelf in a library those are sorted. But my own personal shelf, it's kind of arbitrarily arranged. I've got some graphics books over here. I've got some games books over there. I've got some algorithms books in this pile. And so when I get a new book, I want it to be sort of where I think of it as being. And so I can say, well, if I just put this new algorithm book next to the algorithm books, I don't expect that to make this graphics book no longer be with the graphics books. And so that's what an ordered container gives me, right? A sorted container is a sequential container that has a predefined order. So this is where you see sorted containers. These are the things you get on bookshelves in the library. Those have card catalog numbers, and you look at the card catalog and it'll tell you exactly where this book is supposed to be. So when you're looking for a book and you know that the number to the left of it is less than what you're looking for, and then the number to the right is greater than what you're looking for, if there's nothing in between there, then the book you're looking for isn't available. Right? Another way I could do this is if I take all of the students on the roster and I sort them by ID. There's a function that determines which student goes before the next student, right? You can't just pick a student and say, well, this is a nice sorted list and I've got a new student, so I'm going to put you here in 25th place just because today is a good number for 25. Well, that doesn't work because you've probably broken some ordering, right? So a sorted container has a sequential container, it's an ordered container, but it also has a function that determines how things should be, right? So sorted containers are ordered containers are not necessarily sorted containers. So to clarify here, in an ordered container, elements will maintain their relative position as long as they are not removed. So if A comes before Q and then Z is inserted between them, remember this isn't sorted, it's fine to do that. If A comes before Q and then I put Z in between them, A still is before Q. So the relative order of A and Q has not changed even though we've inserted Z. If Q is removed, the container's still ordered if A is before Z, right? So if I look at, here's my original shelf, I start out with A and Q, right? If they're like that, and then I insert a Z in there. Now I can see that A is before Q, so the insertion of Z hasn't changed the relative order of A and Q. If I then go through and delete Q, you can see that the relative ordering, A is still before Z. The removal of Q hasn't changed that A is to the left of or before Z. So that's really what we're talking about. We're talking about an ordered container. Adding or removing items doesn't change the relative locations of existing items in the container. So as we look at the interfaces of these ordered and sorted containers, we'll sort of look at how they work from other base containers. So the interface here is, let's add some element. In a sorted container, I'm going to have to override the default searchable container insertion, because a searchable container is just something that lets me look through it. Right? If we remember from the previous stage here, it said a searchable container is just a container that holds things and adds a find operation. So if I want to do a sorted containers add element, I can use the add element from the searchable container, but it's not going to do me quite right, because when it's sorted, then I've got to add a little bit more to it. So that's why we say we're going to override the searchable container version to make an add element for a sorted container. In an ordered container, I can just inherit from the searchable container. Searchable container allows me to put things in there. I put them in there, and an ordered container doesn't care. As long as they stay where they're supposed to be, I don't have to do any additional work. All right, remove and find can both inherit directly from the searchable container. That's fine on both containers. Operator square brackets is available in both the ordered and sorted containers, and the withdraw by taking something out, given an iterator for its location. Can I do that? Yes, of course, just as I would do that in some other container. So we don't really have a whole lot of difference between sorted and ordered over the top of searchable, but the sorted container does have to have its own add element because we know that we can't just put something anywhere. There's a particular place where it goes. So the sorted container has to find that insertion location and then put the value there. All right. How about these things? Here's our insertion functions, right? Insert after is not something that you can do arbitrarily in a sorted container. You can't just take any value and say, I would like to insert this after position 4. Because it might belong somewhere else. It might belong after position 14, or it could be the first element because of the sort order. So we can't arbitrarily insert before or after some value in a sorted container. The ordered container, sure, we can do that. We can insert a value or anywhere we like, before or after anything that's already existing in the container, as long as it doesn't adjust the orders, the relative orders of the things already there, it works just fine. So let's look a little bit at implementation. First, we're going to check out our connected memory, then we're going to check out our contiguous memory. We always check these two things out. When we decide how we're going to do it, it kind of depends on what you're doing, right? It's back to the 281 depends argument. So, well, it depends on what you're going to do. Know which operations are going to be called often. That's going to help you decide whether we're going to use connected memory or contiguous memory. We also have to study these multiple implementations so we can understand the asymptotic complexity of each one of the operations. So then as we look at the operations we're going to use repeatedly, we'll know which ones are good. So this is how you make a decision of what you're going to do to implement a particular container. When would a linked list be preferable over an array? There is a time for it. As I mentioned, all of these containers are around because they have some use. So there is a time for a linked list, but in order to use a linked list, you have to defend your need for it. So in this case, if I'm looking at maybe some container where I'm repeatedly doing a lot of insertions in many locations, in the beginning, in the middle, in the end, that's a good reason to maybe use a linked list. How about if I've got very large objects, right? So now if I've got a container that holds a collection of very large objects, these very large objects get to be a pain to move in memory because they're so big, right? You can also think of the fact that the overhead of the previous and next pointer sort of minimizes as my object size grows larger and larger. The importance of those connecting pointers is less and less in terms of memory overhead. So there's reasons why we can defend using a linked list, and you just need to be able to talk about that. So here are our asymptotic complexities. Now we're looking at an ordered container, right? And then as I try to figure out how my ordered container is implemented, I've got contiguous memory here, and I've got connected memory there, right? And so I'll look at each one of these functions and sort of look at their asymptotic complexity given contiguous implementation and connected implementation in an ordered container. Remember, an ordered container does allow me to do insert after and insert before. So add element, I can just do that in constant time in an ordered container. I can insert that value at the end. It's great. In a linked list, I can insert it at the end or at the beginning, I suppose. If I've got a tail pointer, I can do either side. But that should take a constant amount of time in both of those. Because it's ordered, I don't really care where it is. To just add an element just means put it in the container as simply as possible. That can be done in a constant amount of time. Remove something by value. So here we're saying, here's the value I want you to remove. Can you go get that and take it out? In an ordered container, I don't know exactly where that value is, but I can look through it. And since it's an ordered container is going to be implemented over, at the very least, a searchable container, I've got to be able to go look the thing up. So in linear time, I can go find it in the array or in the linked list by nexting to get there. So it's going to take me a linear time to find the value. In the array, it could take me as much as linear time to remove the value, because I can delete some element and then I've got to move all of the other elements back to fill up the space. So the find for remove is linear in either the array or the linked list. When I get to the linked list, I can obviously just cut an element out if I've got a doubly linked list. If I've got a singly linked list, it might be a little bit more challenge, but if I keep track of an extra pointer, I can even do a singly linked list in constant time once I get there. So they both end up being linear. It's just that the linked list's linear is just because it takes that long to find the object, and then it can be removed in constant time, and the arrays takes that long to find it and possibly that long to remove it. So it's just big O of n there. Remove by iterator. This means now I'm not looking at a value. I don't have to go do the find of the value. I'm saying, I want you to remove this thing here that I'm pointing at. Okay, on an array, I still have to move elements to take care of that void as I remove an object. So that's my linear time to adjust the elements around that gap. In a linked list, it depends on what type of linked list I have. If I've given you an iterator to an object in a singly linked list, then, buffering good, bad. Hard. All right. See if I can adjust what's going on in the studio here. It's dropping down to 0 here. Trying to fix this buffering. Sorry, gang. Let's see if this gets any better. Come on, stream. Get healthy. All right. I think I have improved our streaming quality here. It's hard to tell what's going on, but I think we're doing better. All right. So I see we've got a little bit of a discussion about remove by iterator. So the remove by iterator is a function that is just a function that lives on its own. And we're saying the function, when given an iterator to the thing to remove. We don't have to worry about how we got that iterator. We don't have to worry about it taking linear time to find the proper iterator. Maybe you don't have to do a search for the thing you're trying to remove. I'm trying to remove a particular object that I did some other work and I found this object is now expired. Remove this object right here. That's what that one is really doing. Right? So in this case, remove iterator just uses the iterator itself. Right? So in that case, to remove this from an array with our contiguous memory, this is going to take some linear amount of time because I've got to move things back. Right? In my linked list, it depends on how I'm linked. If I'm doubly linked and I'm pointing at some object that needs to be removed, it's quite easy to set the previous object to point to the object after the removed object because you've got two directional pointers. So you can do that in a constant amount of time. In a singly linked list, if I'm pointing at an object and I say I would like for you to remove this object, well, the pointer manipulation that has to happen is if I'm pointing at an object that's going to be removed, I need to tell the object previous to that to point after the object that's being removed. So with singly linked list, I've only got one pointer and I can't jump back. So the linear amount of time to find the previous object is why that sometimes is going to take a big O of n, or other times it could be constant time. The other ones, as we move down, seem a little straightforward. Find and dereference, right? So as I look at those, you can see how find is going to take me a linear amount of time in either situation. I've got to look through the objects because they're ordered, they're not sorted. Operator square brackets, that's random access. I can do that in constant time with my contiguous memory, but my connected memory, if I want to say square brackets 7th object, I've got a next till I get there. So that can be linear in my linked list. Insert after, this one is great. I've got an iterator and a value that I need to put there. In terms of making that happen in an array, I've got to possibly move a bunch of things out of the way. So that's where the big O of n comes in. In the linked list, because I'm just manipulating pointers to insert something after a particular object, I can do that in constant time. So that's how those shake out there. Insert before, of course, I've got the same thing going on. It's going to take me a linear amount of time to move the things back as I insert things before this in the array. In the linked list, now once again it's going to depend on what my links look like. If I've got a singly linked list, then insert before this object is going to be a little bit more difficult because I've got to find the pointer before this, and it could take me starting at the beginning and next until I get to the object right before this so that I can insert before here. If I've got a doubly linked list, I can always just insert in constant time either before or after me. So that's how we look at those in terms of our overall asymptotic complexity. So it's a chart like this that is going to help you decide, hey, I need to implement an ordered container. Should I use contiguous or a connected version of it? Say, well, which things over here are you going to be doing the most, right? Are you going to be spending a lot of time doing these linear removals because I'm giving iterators? Or would you be looking at having a lot of square brackets access, which is going to be constant time or linear? So as you make these decisions, what are you doing? If I've got a list of employees and I'm shooting out paychecks, I don't have a need for a lot of random access. What I'm going to do is every time there's a pay cycle, I'm going to pay everybody. So having this random access might not be as efficient because it doesn't give me anything, right? Or having the fact that I don't have random access in a linked list isn't going to be that much of a disservice because I don't go look for one of them at a time very often. I just start at the beginning and print every paycheck. So you sort of look at your applications and see how that works. Here in a sorted container, similar set of functions. We've just removed insert before and insert after at the bottom because they aren't available in a sorted container. You can't put things in the container arbitrarily. So there's not a whole lot of surprises here. Add some element. This is going to cost me in a sorted container a linear amount of time. Why? Well, it's going to take me probably the fastest I can go. I can use a binary search to figure out where the item belongs. So that takes me log n time. But as I insert it, I've got to move a bunch of other values. So there's my linear time for add element into a sorted container that's implemented by array. In a linked list, the actual insertion is faster. I can do the insertion itself in constant time. However, I can no longer do a binary search. So I have to linear next to find the place where to insert, and then I can constant time insert it. So it's big O of n, just the same. Removal, same sort of thing. Given a value to remove, I can find that in logarithmic time in an array, but it's going to take me, in worst case, a linear amount of time to remove it. In a linked list, I have to find the thing by value, which is just next, and then a constant amount of work finishes that up. But they're both big O of n both of those functions for both of those containers are big O of n. We get a little bit of distinction there when we get into remove by iterator. Once again, if we've got a linked list with 2 pointers, it's pretty easy to cut something out in constant time. Otherwise, both of those containers have their linear challenges. Find is where the sorted container with contiguous memory really shines. We can do this in log n time. And in the linked list, of course, to find any particular value, I've got a next to get to it. So that's a linear amount of time. Operator dereference there, we can do that in constant time in either case. And square brackets, of course, is going to be constant time, give us random access in an array and linear access in a linked list from nexting. All right, we've got started on comparators. I know we've had a bunch of questions about them, and we're still going to be using them throughout the semester, so it's a good idea to learn how to do them well. One of the things that's most important about the way that the STL uses these function objects is it uses them to do the bulk of the work. The algorithm itself is contained by either the container or the function that you're working on, but the vast majority of the work to figure out which object or which thing to be done is done by the comparator. So you want your comparators to be just as lean and mean as possible. You want to have as few conditionals as absolutely necessary. In many cases, you can say, well, a lot of times I'll make a high-level decision in a comparator, or I might think I need a high-level decision. Either do it this way or do it that way. And the question then becomes, can I figure out ahead of time whether that question needs to be asked for every object, or can I ask that question ahead of time and say, rather than, well, I'm going to be doing a bunch of these this way, then it will be more effective to have just a comparator that works for a this way comparator. And then if I'm going to be doing a few of them the other way, I'd have an other way comparator, rather than having a comparator that has a this way or that way option inside of it, so that every object pays the price of deciding this way or that way. So we want to cut out conditionals out of our comparators as absolutely much as possible. We want them to be small and fast. And then I keep saying comparator. I'm jumping back and forth between these names here because we do that pretty flexibly. So let's get a high-level discussion of them. First of all, they're all function objects. It's an object that has been instantiated, that is from a class or struct, doesn't matter, it's an object. But that object also can be treated like a function. And so if you open up operator parentheses and drop argument or arguments in there, then it will behave as a function. So that's what a function object is. And then we've got an abbreviation of that, and we just call those funkdoors. So all of these things are function objects. All of them are funkdoors. Then we've got a couple of particular types of funkdoors that we use. One called a comparator, which is the topic of this slide. A comparator is designed as a function object that takes 2 parameters and returns a bool that talks about whether or not they are in the correct order, right? And the correct order in the STL is always less from left to right. If the thing on the left is less than the thing on the right, you should return true. If the thing on the left is less important or has a lower priority or a lower value, whatever the application is, the STL is looking for less like behavior out of its comparators. So you want to make sure that if the thing on the left is less than the right, you return true. Otherwise, you're going to return false. So there's what a comparator is. A comparator is a 2-argument functor, a 2-argument function object that returns true or false to tell you whether or not things are good. And then the last one that we use quite regularly is called a predicate. We call them predicates. It's a function object. It's a functor that takes one object. It takes just one argument and then just says yes or no. It's kind of like a thumbs down or thumbs up, right? So you look at this object, and if you think this is good, give it the thumbs up. If it doesn't look good, it gives it the thumbs down. So this can be used to filter things. So we'll see predicates, we'll see comparators, we'll see functors, we'll see function objects. All of them are just descriptions of the same or very similar things, right? So for starters, in this one, I'm going to be talking about a couple of things, right? I'm going to see if I can look at the one on the left to see if the one on the left is the one that should be on the left, or the one on the right is the one that should be on the left. So my object that I'm starting with is this struct point, and it's just a simple Cartesian coordinate point. You can think of it as having a couple of integer coordinates x and y. So that's great. I've got a default constructor in there in line 3 that gives me the origin. If I don't ask for it, just give me a point, it gives me the origin. And then I've got a custom constructor in line 4 where I can pass in the x and y coordinates and it will create a new point for me. So that's where I start. This comparator, called compare by y, you see that it is an object. In line 6, it's declared as a struct. Once again, struct or class doesn't matter. They make the exact same object once compiled. The only distinction is what's public and what's private. In a struct, by default, everything is public. In order for a function object to work, it needs to have a publicly available overloaded operator parentheses. That's what makes a function object. An object that has a publicly available overloaded operator parentheses. Any object, you can just add a function on there that has operator parentheses and it's now a function object. It's now a functor. So in this case, I've got this publicly available operator parentheses, and you see that it's going to return a bool, and it also takes 2 objects. So this is a comparator. And it's going to return a.x, look at the x coordinate of a, is that greater than b.x? That's what we're looking at. So we've talked already about
Okay, Dr. Paoletti here now. Hopefully you can hear me. So I'm going to give it just a second so I can see if I get a response that you can actually see and hear me. Okay, so it looks like I've successfully taken over the stream. All right, so sorry about the problems. We'll try to figure out on Professor Darden's end what happened there, and hopefully we can get through the rest of this smoothly today. Okay, so we're talking about funkdoors here, and I was half listening to him while I was editing slides to post for the next couple days. So we've got a functor here if we wanted to say to create a structure, and then we've got a functor. So here's a functor that we can use to, like it says, compare by x. And so this one bases its decision on, is a.x greater than b.x? We could have a different functor that defines it based on y. Now, our functors here, besides being based on x versus y, also make their decisions differently. So let's look at the compare by y first. So in the compare by y, if we use this one to sort, what we're going to get is we're going to get increasing order, of course, based on y. Because less than is sort of the standard functor. So less than as a functor for sorting gives us increasing order. If we then did this based on x, if we did this one, we'd sort in decreasing order by x, of course. So if we change the comparison from less than, so a less than b, we change that to a greater than b, we're sorting in decreasing order. Now, it seems a little bit odd, I'll admit, but this is the way the STL works. It's the way you have to be used to for the project, and especially for part B. So, if we've got this happening, let's look at what happens if we use a priority queue here. So, in this one, if we use this functor for a priority queue, what we will get is we get a min PQ. And if we do this one with a priority queue, we would get a max PQ. And again, max or min based on X or Y. That sounds good. I think his kids are a little young for that. But, you know, hey, never too young to become computer scientists. So, back to this slide. So, when we use the less than less than gives us increasing order for sorting, and it gives us a max PQ. And it's important to understand this because of part B especially. When you do your sorted PQ, if you are given a less than functor and you use the STL sort, you'll get increasing order. But that means that the most extreme element, the highest priority element, would be at the back of the vector. And being at the back of the vector is a perfect place to push, but it's also the perfect place to pop. When someone says pop, you have to get rid of the most extreme element. If you need to get rid of the most extreme element, it's at the back of the vector. And so that works out really nicely for part B sorted. Okay, now we're going to do a little simple example here of binary search. But you shouldn't need the simple example, but what we're really going to do is we're going to be improving binary sort. Oh, that's a good question, Eugene. So the reason that we did this is, hey, I needed to sort my point objects 2 different ways. Or in project 2, maybe I have to order my zombies in multiple ways. I have to order them one order for which order shoot them, but I need a different functor for which order is the least active or most active. So if I just have overloaded operator less than, I can't support 3 different operations easily. So when we have to support different operations, it makes sense to bring it out into a separate structure. It also depends on how other people are going to be using it and what they need to do with it. So binary search, we understand pretty simple. We look at the middle element. If that's not what we're looking for, we look in the left half or the right half, so we look in the right half. Then here we try to split it in half, but it's an even number. We've got the middle, so this is showing how the integer division would work out, is we'd get a smaller left half than a right half. They'd be off in size by 1. But still, we've gone as quick to the middle as close to the middle as we can. So we look at 25, that's not 21, we look left, and we find it. Now, let's look at complexity for this. We've already derived this. We've shown how to do it with the substitution method. We get log n. And for this to happen, the elements have to be sorted before we can do a binary search. So here's a set of code that works for our binary search. One thing important to understand about this, and we're going to try to stay this way throughout the searching slides here and a bunch of sorting slides that are going to follow, is when we say here left and right, these are indices, and they are of a sense left is inclusive, right is exclusive. So we're going to try to stick with that format of understanding iterators because it's what's consistent with the STL. And so that being consistent keeps us a little bit, it makes things a little bit easier to remember. Okay, so we're given an array of doubles. We're given a value, a double value to search for, and a left and right index. And when we start out, I would call these with 0 and the size of the array. So that's my left end is index 0, my right end exclusive is the size. So if there were 5 elements, I would call it with 0, 5, and then that means that index 5 is not actually part of it. We go 0 through 4 inclusive. Okay, so while right is greater than left, basically line 3 is saying while there are places left to search. So while there are places left to search, we go to calculate the middle index. Now the way we calculated this middle index is a fairly standard way of doing it, because if we tried to add left plus right and then divide by 2, we could have really big integers that actually overflow the range of an integer. So if we had on the order of a little over 1 billion elements in here, we might overflow if we did like left plus right over 2. So this works out a little bit better if we have a huge, close to integer max, integer number of elements. It's also, this arithmetic works with pointers, where if we had pointers, you can't add pointers together, but you can subtract them. So this would work if we were given pointers, or if we were giving random access iterators, this would still work. So we figure out where the middle is, and then we say, hey, is that middle element the value I'm looking for? If it is, let's return that middle index. Otherwise, I decide whether I should move the right-hand end. So if the value I'm looking for is smaller than what I find at the middle, I move the right-hand end. Otherwise, I move the left-hand end. And notice here, remember the mid was already included in the search, but when I change right, right is exclusive. So when I move right to be equal to mid, I don't look at that middle element again. When I move left, though, I have to move, because left is inclusive, mid is here, left, sorry, that's supposed to be square, left is going to be 1 plus mid. So left is going to be included, right is not. Now this works, it's log n complexity just like we would expect. But the question is, and there's a breakdown of our sort of constant steps, we're going to loop k times, k is equal to log n. Now, we can improve this. We can't make it better than log n, but we can reduce the constants a bit. Now, there's a question here, how would we compare elements that are objects? So we want to do a little bit of modification to this to look at comparing objects before we go and look at how to improve binary search. So let's say that this wasn't an array of doubles, let's say this was an array of students. All right, and then when I'm searching this array of students, would I search for, so I had to change the type of the array, would I say, hey, here's a student. Here's Marie Jones. Marie has a GPA of 3.872. She lives at this address, this city, state, zip code, blah, 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 blah. Would I give it a whole student object to search for? Probably not. If I know all of that stuff, I pretty much know she exists and I know everything about her. So instead, what I might do here for the value to search for is I might say, hey, let's change this to a string. Now, sure, we could do const string reference, but it's getting a little crowded here. So we say, hey, here's a string. I want to search for Marie Jones. I want to search for this student by name. So we're going to have to change our comparisons on values. I can't compare a string to a student object at line 5. What I would do is I'd say, hey, let's change this to a sub mid dot get name. And I'll do the same thing in line 8. I would change this to dot get name, parentheses, and I got to close the parenthesis there. So I change those to dot get name, and now we can search for a particular student by name. And maybe I'd change the function, like binary search student by name or binary search student by U of M ID. And for this to work, they would have to be sorted in the same order as the thing I am searching on. So yes, if we wanted to make this more complicated, we could go and add a comparator to this. If we use recursion, no, we'd still get log n. We'd just have a slightly bigger constant in our log n. Okay, so here's what we're going to do. Simple observation is that the equal being true, it's rarely true that it's equal. It's more often that it's less than or greater than. We usually don't get lucky on the very first try. It usually takes a couple of searches before we find the one we're looking for. So the first change we're going to make is we're going to just reorder our comparisons, do less than followed by greater than, and then equals would be last. If it's not less than or greater than, then it must be equals. Now, a more extreme idea would be to say, hey, let's get the equals equals out of there entirely. Not only am I not going to compare for equality, I don't care about equality. I'm going to find the lower bound of the value searched for. I want to find where it is or where it would be if it was there. So if we go back a couple slides to this one. So if we go back a couple slides, if I asked you what is the lower bound of 21, it would say here. Here is where 21 would be or is if it's there. If I said search for the value equal to, say, 18, it would also say here. It would say, it's saying if 18 was there, that's where it would be. So that's what we're going to do, is we're going to change it to find the place it is or the place it would be, and we don't care whether it's actually there or not. So we're going to worry about the equals equals after the loop, after we find where it would be. Okay, so here's our comparison. So it says at the top, almost always 3 comparisons per loop. So let's count our comparisons. We've got 1 comparison on the indices. That has to be there. We've got to make sure there's still places left to look. Then I check if it's equal, then I check if it's less than. So that's 3 comparisons, and it's almost always 3. The only time it's not is when we get lucky and we find it, the one time we find it. So this is before. It's almost always 3 comparisons. If I reorder this to do the less than and greater than and then the equality is implicit, so now I have, it says 2 comparisons half of the time. Now I said 3, I don't know why it says 3, that really should say 2, because we're sort of counting. 1, 2. I think I copied and pasted too much. Okay, so, actually no, so because we've got the other one commented out. So we got the grade in the comment here. So check number 1 is the index, check number 2 is less than, check number 3 is the other less than. So notice, instead of checking greater than, I check less than in the opposite direction. Because if I'm saying, is A greater than B, that's the same as asking, is B less than A? And we say B less than A because this is what the STL tends to do. It doesn't try to force you to support both less than and greater than. If it can, it would like you to just support less than. So if I just reorder my comparison, I can say, if I have to look in the left half, else if I have to look in the right half, else it must be equal. So this one says it's 2 comparisons half the time. So this comparison has to happen, that comparison has to happen. But if comparison 2 is true, then comparison 3 doesn't happen. So about half the time we will have to go to line 8, but half of the time we will stop after line 6 and go straight to line 7. So 1 and 2 always happen, but if 2 is true, 3 doesn't happen. 2 should be true about half the time. So we've gone from 3 comparisons almost always to basically an average of 2.5 comparisons. And now what we're going to do is we're going to change this a little bit more. And we're going to change the conditions also. So here we've got test 1 is the same, test 2 is the same, and the assignment is the same. Left equals mid plus 1. Else, we know it must be greater than or equal to. Because we know it might be greater than or equal to, we set right equal to mid. Because mid has not been completely checked. It might be greater than, it might be equal to, we don't know. So we set right equal to mid here. Now, when we're done, we return left. We always return left. We never return mid. So let's go back to our example. I think I'll draw an example in here, which will give us, I've got a slide on the next slide for this, but we can't see the code there, which makes it a little bit harder. If we're in a lecture hall, I can put this up on the board for part of the work and leave the slide up. So let's do a quick example here. Let's say I had, let's see, what's my values in the other one? 2, 3, 5, 7, 13. 2, 3, 5, 7, and 13. Okay, so let's say I'm searching for the value 10. So I'm searching for the value equal to 10, and I look and I calculate, is right greater than left? Okay, let's keep track of where are right and left now. So left is over here, and right, let's pretend right is not exclusive. It'll be easier to draw. Let's pretend that right is inclusive. It'll make this easier. So we calculate the middle. Middle is here. We look there, that's not 10. So is a sub mid less than the value? No. So we set right equal to mid. Or wait, sorry. Is a sub mid less than the value? Yes, sorry. So is a sub mid less than the value I'm searching for? Yes, it is. So I set left equal to mid plus 1. So that's not left anymore. This is left, and that's not mid anymore. So is right greater than left? Yes, it is. So we still have places left to search. So we go back through the loop, and we I'm going to move right. I realize here we're going to run into an issue with our comparison. So yeah, let's do right exclusive. Okay, so we say is right greater than left? Yes, it is. So figure out the middle. Okay, where would the middle be? It'd be left. So left is index 0, 1, 2, 3. So we've got 3 plus 5 minus 3 is 2, divided by 1 is 1. So mid equals index 4. So we set middle is equal to index 4. Oh wait, no, let's see. 0, 1, 2. Okay, so left is 0, 1, 2, 3. 5 minus 3 is 2, 1. So middle would be index 4. Okay, so middle is there. So right is off the right end, middle is there. So we say, is the a sub mid less than the value we're looking for? A sub mid is 13. Is that less than 10? Yes, it is. So we move, or no, it's not 13. Is 13 less than 10? No, it's not. So we move right over to where mid is. Oh, wait a minute. So we move right, so right isn't there anymore, right is over here. Now, we go back through the loop. Is right greater than left? Yes, it is. We figure out the middle. So the middle would be left is 3 plus 4 minus 1 is 1, divided by 2 is 0. So mid becomes now, mid is here. Is a sub left, is a sub mid less than the value I'm searching for? Yes, it is. So I move left up to be mid plus 1. So left moves here. We go back to the top of the loop. Is right greater than left? No, it's not. Because it's not, we drop out of the loop and we return left. We return left is saying basically that's where 10 is, or where it would be if it was in here. So that's the example I intended to run through on here, but we didn't quite have room for that and the code in the same place. So if we search for 10, we find where it would be. And if we went through this and searched for, say, 13, it would return the same one. It would say this is where 13 is. So we've found a lower bound. We've found It works out, Alex. If you look at the same example we just did with searching for 13, we'd get the same result because there's only one place left where it is or could be. Okay, so in the STL has a function called binary search. Binary search, I would say, is less than useful. Binary search in the STL returns a Boolean. It says true or false. It's in there or it's not in there. What the STL also has is lower bound, upper bound, equal range, and you can look these up. The lower bound is basically equivalent to what we just wrote, except it's written by the STL people and it uses iterators and it's more confusing to read. But it basically does the same thing. It uses a left that's inclusive, a right that's exclusive. It finds the place where it is or where it would be. So if we had duplicates, so if I had something like 2, 3, 5, 5, 5, and I asked for what is the lower bound of 5, lower bound of 5 would say here. That's where 5 is or where it would be. It is the last possible place a 5 could be. And let's say there was an 8 over here. Well, then what would the upper bound of 5 be? The upper bound of 5 would be here. That's the last place 5 is or could possibly be. Now, equal range tries to find a group of elements that are the same as the element you're looking for and basically returns. So, or equal range is kind of like doing lower bound and upper bound. It gives you both iterators. And it's always inclusive, exclusive. So even lower bound and upper bound, they accept inclusive, exclusive as their iterators. They return inclusive, exclusive range. So the lower bound is an inclusive, the upper bound is potentially exclusive. This also works if there wasn't an 8 in there. If there was nothing else, it would say this at the end of the container is the last place that 5 could possibly be. And again, we have an inclusive, exclusive range. Now, when we use lower bound and upper bound, it's important to understand what does the STL expect to be given. So these expect, I've never actually used equal range, but I assume it's the same parameters. But I know lower bound and upper bound are the same parameters. So lower bound and upper bound, we need to give it a begin iterator, an end iterator, a value to search for. And optionally, so there's two versions. There's one that accepts begin, end, and a value. There's another that accepts begin, end, a value, and a less than functor. And the second version uses that less than functor. Instead of doing less than on the values, it uses the functor you give it to determine where the value is or should be. Now, this is really important for Project 2, Part B, sorted PQ. So when you want to say, hey, I'd like to push, I've already got a container that's completely sorted. I need to add a new value to this container. Well, I've got to find out where that value should be. I don't care if it's in there or not. I just want to know where it should be. So you could write your own binary search, but it would end up being a little bit slower than the STL. You use the STL lower bound. What does it return? Remember, these are iterators, not indices. What it returns is it gives back an iterator. So it returns an iterator, but hey, that's great for you in sorted PQ because you want to say, hey, data vector. Oops. T-A-T-A. Hey, data vector. I'd like to insert something. I'd like to give you an iterator where to insert and a value to insert. And so that iterator is basically what came out of lower bound. You give that iterator to the insert to put it there. And so pushback can really be written and one line of code. Okay, we're going to look at using a container, doing a types of operations, and we're going to actually go through the code for one of them. So we're going to use this container as an example of a set. So a set is well defined if you can tell if any given element is in the set. So we want to be able to tell you, hey, this element is in the set or this element's not in the set. We're going to keep a simple definition of sets here. We're going to try to use no duplicates. Makes the code a bit easier when we get around to coding it. So if we had sets, we could do union, we could do intersection, we could do set difference, symmetric difference, only in one but not the other, which is called XOR, and also really simple things, obviously, like is it an element? Is 5 in this set of integers? Is your set empty? I'd like to add an element to this set. So as an example here, and this may look terrible on your PDF because it's an animated slide, so I think the PDF got condensed down to one slide with lots of arrows over the top of it. So we start out, and I've got set 1 and set 2. We're going to make another restriction. Our containers that we're going to do set union on must be sorted. It's going to make things a lot easier if the container is sorted, and like I said before, no duplicates. So we've got iterators into the beginning of set 1 and set 2, and set 3 is where I'm going to put the union. Let's pretend that set 3 is a container that's big enough to hold the union, and I've got an iterator into that container. And right now there's nothing in there. It's just, it's allocated, but it's not, any values have been stored in it yet. So we look at Amy and Amy, and to do a set union, we would put one Amy in the output, and we would move all the iterators forward. Now I look at Beth and Blake. They're different. The smaller one, Beth, goes to the output. Beth's iterator has to move. The output iterator has to move, but Blake's iterator stays where it is. Then we've got Brian and Blake. Okay, the smaller one, because the inputs are sorted, the output's going to be sorted also. The Blake gets copied to the output, Blake's iterator moves, and the output iterator moves. Brian and Bob, Bob's the smaller one, Bob gets copied to the output, Bob's iterator moves, output iterator always moves. All right, I got Brian and Brian. Two Brians, we copy one Brian to the output, we move all the iterators forward. Now we've reached the end of container 2. We don't have to do any more comparisons. Since we're doing a union, everything left in container 1 gets copied over to the output, one value at a time. And when we're done, the iterator on the output points to just past the last thing that got written. And that's in the STL sense, is I started out, I know that the start of the output is here, that's inclusive. The end is exclusive. It's everything from the start of container 3 to wherever the set union left off and told me the iterator. Okay, so code. Lots of code here. Big wall of code. We're going to go through it a piece at a time. So we start out and it says we've got a template. Okay, yep, we got to do templates because I don't know what the containers are or whether they're iterators or what. So I've got a template. I've got template types are for iterator. For iterator is shorthand there for forward iterator. I couldn't quite fit forward iterator onto lines 3 and 4. This one I could have rearranged and put the output iterator on its own on the line with the compare, but forward iterator didn't fit on lines 3 and 4, and I didn't want to make the font size any smaller on this. So we've got forward iterator type 1, forward iterator type 2. Those are our iterators into containers 1 and 2. Now you might ask, why do we have two different types of iterators? Well, what if this was, set 1 was a vector of string, and set 2 was a linked list of string? Then that allows for two different types of inputs. They're still both required to be sorted. They're both required to have no duplicates, but they could be different underlying types of containers. And maybe set 3 is dynamic memory, or maybe set 3 is a deck of string objects. And we're going to assume that it was big enough to hold it. We'll talk about fixing that afterward. Okay, so that's why we have multiple types of iterators here. I've got my forward iterators into set 1 and 2. I've got my output iterator into the output container, and I've got a comparator, this funkdoor that I'm going to use for doing comparisons. Now, the forward iterator, let's remember what it means. Forward iterator means we're allowed to, all iterators can be copy constructed, so we made copies of the iterators here. All iterators are allowed to be dereferenced. All iterators are allowed to be plus-plussed. A forward iterator, we can read from it, and we can read from it multiple times before we plus-plus it. So when we dereference a forward iterator, we're allowed to read, and we are allowed to read more than once before we plus-plus it. For the output iterator, when we dereference an output iterator, we are only allowed to write, and we are only allowed to write once before we move forward. We cannot read from the output. We cannot store multiple times before moving forward. We can write and move forward. Also, forward iterators can be compared to others of the same type. Output iterators cannot be compared, and it doesn't matter if here because there's nothing else of the same type to compare it to. Okay, so let's go through the code. So we've got the template taken care of. Line 3 says, hey, I've got first one and last one. So first one and last one are our iterators into the beginning and just past the end of set 1. First 2 and last 2 are the beginning and end, the beginning and just past the end of set 2. Output iterator, we called it result. Result is where we're going to put our output. And we've got our type compare is named compare. So when we want to compare things, we're going to use this thing called compare. The PQs, yes, allow duplicates. Okay, so our while loop here. While loop says while first one is not equal to last one and first 2 is not equal to last 2. So that's saying while there are still things left in container 1 and there are still things left in container 2. Why not equal? Couldn't we just do less than? Sure. No. This one would compile and this one would fail to compile because vector iterators support less than, linked list iterators do not support less than. So we're not going to do less than operations here because it won't always work. Sometimes it will, sometimes it won't. So when we do comparisons of iterators, we want to stick to equal, equal, or not equal. Those are guaranteed to exist, but less than is not guaranteed to exist. Okay, so while we are not at the end of the first container 1, while we're not at the end of container 2, we call compare. We say, hey, let's compare what's in container 1 to what's in container 2. Notice the dereference there. So the compare accepts things that are in the container, but the iterator, we have to dereference the iterator to look at the contents. So we're basically saying here, what it says in the comment in line 8 is set 1's element, we're asking the comparator, is set 1's element less than set 2's element? If it's true, then what goes into the result, let's break this down a piece at a time, what goes into the result comes from container first 1. Then the post increments happen and the result iterator moves forward, first 1 moves forward. The order of operations here is correct, and we can't modify it with parentheses to try to make it clearer. So the dereference applies to the iterator, the plus plus applies to the iterator. If we try to add parentheses to say, well, I don't like reading it this way. I want it to say dereference first 1 plus plus. Well, now first 1 gets dereferenced, we read from it, Then the plus plus applies to the dereferenced value and changes the value, and we never move first one. Now we've got an infinite loop of trying to plus plus a string object. Oh wait, that didn't even compile because we're not string operators. String objects don't have a plus plus operator, so we can't add parentheses to make it more clear. So what happens there is the dereferences happen first. So really the order here is we dereference and find where we're reading from. We dereference, find where we're writing to. Then the assignment happens. Then the plus pluses happen. And the order of the plus pluses, I wouldn't want to guess which one happens first. I don't think C++ forces an ordering there, and I don't know and I don't care. I never want to worry about that level of detail. Okay, so if set 1 was smaller, we copy set 1 to the output, and set 1's iterator moves, the output iterator moves. Else if compare of dereference first 2 and dereference first 1. Remember when we did that earlier where we wanted to say like, hey, is A greater than B? But because we only have a less than comparator, instead we say, is B less than A? So we use compare. Compare only answers the question less than, so we reverse the operands. We say, is what's in set 2 less than what's in set 1? If that's true, we copy from set 2 to the output result, and then we move both iterators. Else, and we saw this when we were in the middle of modifying binary search. If A less than B was false and B less than A was false, then the two must be equal. So if they're equal, we copy one of them to the output. It doesn't matter which one. I could swap 1 and 2 here and the code would still be fine. So we copy one of them to the output and we make sure that all of the iterators get incremented. So the result iterator gets incremented, first 1 gets incremented, and then first 2 gets incremented. Now, in this line, in line 13, I did it as a pre-increment. I did pre-increment here because pre-increment is actually slightly faster. In line 12, I did it as a post-increment, 1, because I don't want to increment before I look. I've got to look, copy, and then increment. And I didn't want to write line 12 as 3 lines of code with an assignment and then a plus plus and then another plus plus. I didn't want to use up 3 lines of code for that, even though it's very slightly slower. But you'll tend to see the STL tends to use this line, line 12, the way it is, even though 3 separate lines would be very slightly faster. So we increment all 3 of the iterators, first 1, first 2, result all get incremented because this is the case where we had something like over here when we had Brian and Brian. We copy one of the Bryans to the output and all of the iterators move forward. Okay, then that's the end of our while loop. As long as there's stuff left in container 1 and 2, that while loop keeps going. When that while loop ends, we know we've reached the end of at least one of the containers. Then, while container 1 still has stuff, send them to the output. While container 2 has stuff, send it to the output. At most, one of those is going to run. If we reach the end of the while loop here, it's because at least one container ran out of stuff. They could have both run out at the same time. If we had had this case, where that was the end of the container, we'd copy Brian and Brian. We'd copy one Brian to the output. We'd move both iterators forward. We'd reach the end of all of both of the input containers at the same time. So that could happen, or maybe we reach just the end of just one of them. So at most one of those loops is going to run, copy the remaining stuff to the output, and then we return result. And it says the end of the sorted union. Remember, the end of the sorted union is always exclusive because we always store into the output and then we post increment to move past what we just wrote. So it's the result iterator here is always just past the last thing written. Okay, so I haven't seen any other questions on this code, or any questions at all on this code. So let's look at how we would use it and how we would change it. So how we would use this. So I would have to remember what iterator it gave me. So I would have to say, well, what is it? It's auto. Auto iterator equals my set union of stuff. We're going to get to that in just a second, Evan. That's what we're doing now. So I'm going to get that iterator, which shows me where we ended up. Now, let's look back in the previous slide here. When we got to the end, erase all my marks here. When we get to the end, the output iterator points here. Now, let's look at how big, before we worry about how we're going to use it, let's actually worry about how big these had to be. So set 1 has 1, 2, 3, 4, 6 elements. Set 2 has 4 elements. How big did set 3 have to be to guarantee this would work? Set 3 had to have room for 10 elements. Because if they were all distinct, all of them would have got, if they were all distinct, meaning all different, all 10 of them would have been copied out to the output. And we would have had to have room for all 10. But because there were duplicates, because there were 2 Amy's and 2 Brian's, we only ended up writing 8 of them out. But I want to know where the end of that container is. So that's why we need that return iterators, to know where we left off. But wait a minute, set 3, like we said it, hey, we said set 3 was a deck. Set 3 was a deck, we resized it to 10, but now it's got 2 empty strings at the end of it, and I don't want those empty strings there. So what I can do afterwards is I could say something like set 3 dot erase where? From it to set 3 dot end. Now what would I give this? I'd give it set 1 dot begin, set 2 dot begin, or sorry, set 1 dot end. So I'd give it set 1 begin and end, set 2 begin and end. I'd give it the output iterator, I'd give it set 3 dot begin is where to put it. And then I would give it my funkdoor, which we never wrote. So that's what I would give to it. It wrote it into set 3, which before this I had to resize set 3. I had to say basically set 3 dot resize to be as big as set 1 dot size plus set 2 dot size. And semicolon. Okay, so I had to resize it to begin with to make it big enough, and then I had to erase the unused portion. And this erase is, in the sense, inclusive, exclusive. So erase from where it left off at the iterator that was returned, erase from this point to the end, inclusive, exclusive. So that got rid of those 2 extra spaces. Now that's a little bit painful to resize it first and then erase the elements again at the end. There's a slightly easier way to do this, and I'm running out of room for places to write here. So literally erasing down at the bottom. What we can do is, instead of resizing container 3, so when I do set union, I could do the set 1 begin and end, set 2 begin and end, and I would do comma back underscore inserter parentheses set 3. And we'd have to give it the funkdoor. So back inserter comes from, I believe it's called the iterator library. Look up back underscore inserter. What back inserter does is it's like this wrapper for an object. So when we use result here, when we do things with result like dereference and store into it and plus it, the back inserter takes care of adding to the back of set 3. It basically does a pushback on set 3 and takes care of all of the bookkeeping for us. So with this one, we don't have to resize set 3 beforehand. We don't have to resize set 3 after we're done. We just have to use a back inserter on set 3. So you can look up back inserter and see how to use those. Now, you can scroll back in here if you've got any questions later on when you go through the video. I'm going to have to erase everything here if we don't have any more questions. I'm going to give you a few seconds to come up with questions because I've got to erase everything here to change this. We're going to look at changing this to make it do something different. Okay, so while I wait for questions, let's talk about what we're going to do with this. So this was set union. What I want to do is I want to turn it into set intersection. So we'll wait for questions, and I'm not going to erase just yet. What I want you to also do is start thinking about what would I have to do to change this to produce a set intersection. And I'm going to do the easy one for you. I'm going to change the function name to set intersection. So other than the easy one, what's the hard stuff that we have to do in here? So start thinking about that. You can type some answers in. If you've got a question before I erase all my notations on here, go ahead and ask that, and I'll give you a minute to think. Okay, so I haven't seen any questions yet, so I'm going to go ahead and erase all of this stuff, and we're going to look at changing this. Okay, so we'll change the name to set intersection. Okay, so we change the name, then we've got to change what happens. So when we get set 1 element is less than set 2 element, when we're doing set intersection, do I want to send that to the output? No, I don't want to send it to the output. I don't want to change the output at all. Therefore, I don't need to read from it. All I have to do is increment first one. And then same thing when the set 2 element is less than set 1's element. We're not going to put anything in the result. We don't need the equals. We don't need the dereference. We just increment first 2. So if element 1 is less than, we move set 1's iterator. Else, if element 2 is less than, we move set 2's first iterator. Else, when they are equal, we do the same thing. We do we leave the code alone. We do the same thing as set union did. We copy one of them to the output. We make sure everybody gets incremented on the iterators. Now, what about for the last 2 loops? Exactly, Kevin, that's what we're going to do next. So these last 2 loops, those are just going to get eliminated entirely. We don't need those at all because if there's something left over when we reach the end, There can't be any intersections left to do. When we reach the end of one of them, we must be completely done. We still return result. We got to have that line, but we can get rid of those loops. So really, set intersection is just a lot simpler than set union. Now, how big, here's another question, how big, if I'm doing set intersection and I'm not using a back inserter, let's say I did it in dynamic memory and I had to new a block of dynamic memory, how big would I have to make my block of dynamic memory in order for this to work? How big does the output have to be for set intersection? So set union, it was the sum of the two. For a set intersection, you've probably already thought of this, you're just like behind me by like 30 seconds. For the set intersection, the output would have to be the minimum of the two sizes. So if there's 1,000 elements in one and 3 in the other, we can't have more than 3 matches. If we use back inserter, we don't even have to worry about that. We let the back inserter grow it as things get found that are going to be added to the output. So we've got some notes here on complexity. So if I want to initialize a set with a range constructor, or sorry, with ranges and stuff. So when I want to initialize a set, it could be O of 1 or it could be O of n log n, depending upon whether I'm making an empty set or the range-based constructor. And really I'm saying like default constructor or range-based constructor. The range-based constructor, I would have to sort what you give me, and I would have to get rid of duplicates. And the sorting takes the bigger part of the time there, n log n. If I want to clear a container, it could take O of 1 or it could take O of n. O of n is because what if I had to run destructors? What if I had a container full of strings? When I do a delete on the underlying dynamic memory in, like, say, my underlying container was a vector, vector destructor actually can take O of n if it's objects that have a destructor. Destructors all have to run. I want to know, is something a member of this set? Log n, I can do a binary search, or, whoa, better yet, lower bound and make sure it really is there. If I want to copy a set, it takes O of n time. However big the set is, that's how long it takes to copy. Set union, set intersection, O of n. Well, wait a minute, what is n here? N is going to be the combined, for both of these, the combined sizes of both containers. When we do set union, it was easy to see why we had to look at everything. When I do set intersection, think about if I had a container that was filled with names starting from A through Y, and then container 2 had one name that started with Z. I would still have to go through everything in container 1 before I get to the end of container 1, and that's still basically O of n minus 1 is O of n. And this is the maximum. Set intersection could end really, really quickly if the first container starts with B, so if I had something like B through Z, and this container had one entry that started with A, I would say, hey, move past this one. Oh, look, I'm done. I finished quicker. So this is O of n is our, because we used O of n here rather than big theta because it's the worst. It could be as bad as O of n. Could be faster, but it could be O of n if we reach the, it could be O of 1 if we reach the end of one of them quickly. Okay, another topic here, and I'm sorry we're going a bit over because of the whole buffering and switching over thing. So we're going to look at this topic, and we're going to come back to this one later on. So suppose I want to represent disjoint sets, and my example here is we're sending colonists to Mars, and we start making little enclaves of little tiny settlements, and we start connecting them with like little outdoor railroad lines. You still have to wear your spacesuit, but you don't have to walk. You can get on the little electric tram and take it over to the other colony. When we start doing this, we are not going to be able to afford the luxury of cycles. So, and the Mars names here get a little bit hard. So if I want to go from Tharsis Montes to Tempe, I can get there. I can go through that link and through that link. Having a direct link between those two, that's a luxury on Mars. We can't afford that. So we are only going to connect things that are not already connected. So when I say, hey, can I connect Tharsis Montes to Tempe? We'd say, no, they're already effectively connected. Can I connect Tharsis Montes to Valmaraneris? We'd say yes, because they are in disjoint sets. The disjoint sets could now be combined into a bigger set. So if I run a rail line across from there, then hey, maybe I should recolor these as red now, because hey, they're all part of one big set. That's the red set. So I should have moved forward. I forgot. We've got numbers. Numbers are easier. So I want to connect settlement 23 to settlement 10. Yes, I can do that. So we've got these disjoint sets, and we've got all the single sets. Like 18 doesn't even have a settlement yet at all. It's a location. Or maybe, hey, maybe 18 is a settlement that just isn't connected to anybody yet. So I could run a rail line from 18 to anybody I wanted to. It would be valid to do that because it wouldn't produce a cycle. So in this idea of determining, can I lay a new rail line to connect these two locations or not, there's two basic operations here, find and union. Find says, what set are you in? So I basically union, what union is going to do is it's going to call, so I say, hey, I would like to do a union of 3 and 10. Union would call find twice. Union would say, hey, let's find out which set 3 is in, let's find out which set 10 is in, and oh wait, look, they are in the same set. Union would say, no, you can't merge those together. If I said, can I do a union of 10 and 23? It would look at 10, see 10 is part of the red set, 23 is part of the blue set. Not only would it return true, but it would also modify its own internal data structure to keep track of the fact that 10 and 23 are now linked and are now effectively part of the same set. So when we do that, we've got these two operations, union and find. This is called a union-find data structure, and this comes up with different problems. And we're going to see a real application of this later on. It may not be on Mars, but it is going to be with connecting things. So we want to know how we can efficiently implement these two operations. And we also want to consider the cost over the entire lifetime of the settlements. So we go from n single sets of size 1 up to one big superset where everybody is connected together. So that's we're worrying about the whole long-term complexity of going from all disjoint up to one big connected set. So first example is, what if they are separate containers? What if I have a group 1 container, a group 2 container, group 3 container, and what if I have a container to hold all the containers? Well, then when I want to know if 1 and 8 are connected, I've got to look at every container in my container of containers and look through everything in that group and say, is 1 in here? So maybe the order is, when I look at my outer container, maybe the first thing I find is group 3, and then I find group 7, group 12, group 18, group 23, and then I find group 1, and then I search through group 1 and I find that 1 is in there. And then I search through all of those other containers. When I get to container 1, group 1, I search through, I find that 8 is in there, and I say, no, you can't do a union of 1 and 8 because they're in the same container already. but maybe I had to search through a bunch of other groups just to find that out. If I ask about 1 and 6, I search all these containers until I find the group containing 1. I search all of these containers until I find the group containing 6. Then I say, oh, group elements 1 and 6 are in different groups. They can be combined. How do I combine them? Well, then I would have to say, well, let's add, let's go through the smaller one. Let's take 2 out of this one and insert it here. Let's take 6 out of this one and insert it there. Let's take 7 out of that one and insert it there. And then let's eliminate group 2 from the container of containers. And that's a lot of work. So using disjoint containers is a lot of work to do the find, and it's a lot of work to do the union. Terrible choice. Union is O of n, where n is the number of elements in all the sets. N is the number of basically settlements on Mars. Union is O of n, find is O of n, it's all O of n, and we're going to have to do this n times successfully. We could have unsuccessful queries that take O of n time, but to get from n disjoint up to one big superset containing all of them is going to take n minus 1 successful unions. So it's going to take n minus 1 successful unions and maybe a bunch of unsuccessful ones where I said, hey, can I connect these two? I do O of n work, and it says, no, you can't connect those. They're already connected. So that would be O of n squared if we do this n minus 1 times successfully. We don't want that. That's n squared is too bad, too long. So first idea is, instead of making a container of containers, let's make everyone know a representative. Which settlement is the representative of your cluster? And so then everybody in that set must know who the representative is. But then find becomes really fast. I just say, hey, element 1, who's your representative? Element 6, who's your representative? If you have different representatives, you're in different groups and you can be combined. If you have the same representative, you're already in the same group, and no, you can't be combined. So if with this idea of just being able to look up someone and know who their representative is, find becomes really fast, but union is still kind of slow. And so there's an example here we could run through a little bit of this. So I say, hey, I would like to do a union of 1 and 3. So initially, what's everyone's representative? Everybody is their own representative. When I will say, hey, I'd like to join 1 and 3, I say, 1, your representative is 1, 3, your representative is 3. Oh, you have different representatives. You can be joined together. And to do that, I have to update one of the sets to have the same representative as the other set. I'm going to choose to always update the second one arbitrarily. So I've got to update this one. You say my representative is now 1. If I want to join 3 and 8, we ask 3, who's your representative 1? 8 says 8. They are different. They can be unioned. 8 changes its representative to be 1. And we could draw this over here. So everybody initially says themselves. Now 3 says 1 and 8 says 1. Okay, I want to join 1 and 5. 1 says 1, 5 says 5. They have different representatives. 5 can be changed to say my representative is now 1. Okay, what about 7 and 4? 4 says 4, 7 says 7. They have different representatives. Therefore, the second one, 4, can say my representative is now 7. Okay, can I join 7 and 2? 7 says 7, 2 says 2. 2 can change its representative to be 7. And now I say, can I join 2 and 5? 2 says 7, 5 says 1. They have different representatives. But now, to make this, so 2 says 7, 5 says 1, They are different, so the union can happen, but to make my own internal data structure correct, I've got to update everybody in group 1 to be part of group 7. Well, how do I find everybody in group 1? I don't have a way, so I've got to look at everybody and say, are you in group 1? Oh, you are? Okay, change that to a 7. Are you in group 1? No. Are you in group 1? Yes, change that to 7. Are you in group 1? No. Are you in group 1? Yes, change that to 7. Are you in group 1? No. Are you in group 1? No. Are you in group 1? Yes, change that to 7. That took me O of n time just to complete the union. Too slow. So having the find be really fast is nice, but having the union be really slow is bad. Okay, so we could say, like we said before, let's update the smaller set. We already found that doesn't help us because I still have to look at everybody. So this idea doesn't help at all because I don't know where the smaller set is. I don't even know which set is smaller. I don't know where it is. I got to look at everybody. So that doesn't help. Okay, how about if it's okay not to know the ultimate representative of your group? It's okay if you know someone who knows someone who knows someone who knows who the ultimate representative is. So now union is going to get to be a little bit slower, or sorry, union is going to get to be faster because there's less updating to do, but find is going to become slower. So find becomes slower, union becomes faster, which is a good progress. So let's look at an example here. So initially, everybody has themselves as their own representative because everybody is their own disjoint group. Okay, so I want to join 1 and 6. So 1 says 1, 6 says 6. We say update 6 to be 1. We're good. Join 1 and 8. 1 says 1, 8 says 8. We change 8 to be 1. We're good there. Join 1 and 3. 1 says 1, 3 says 3. We change 3 to say 1. Good. 5 and 6. 5 says 5, 6 says 1. Well, let's just change that. Let's just say, okay, so 6 says 1, and so they are different groups. If I change 6 now to say, hey, 6's representative is now 5, we've made it happen, but now look what happens later on. So I say, can I join 4 and 7? 4 says 4, 7 says 7. They are disjoint, so yes, I can update 7 to say 4. Can I join 4 and 2? 4 says 4, 2 says 2. 2 can become part of group 4. And now I try to join 5 and 4. 5 says 5, 4 says 4. Okay, so I just change 4 to say, oh, well, 4 is now part of group 5. This works fine, except now if I try to do a union, if I try to do a union that involves, say, who hasn't been joined with anybody? One and 2. So if I try to join 1 and 2, 2 says 4, 4 says 5, 5 says 5. I had to go through a long string there. So the find takes a bit longer, but union gets really fast. So that works. Union gets really fast, but find can be slow because we can have a big stick. If 8 says 7 and 7 says 6 and 6 says 2, etc., we can have a big stick for find on that O of n. So we'd like to be better than that. So what we're going to do is we're going to make a change here. We're going to keep the old idea of I know someone who knows someone, but if we ever ask anyone who's your representative and they don't really know who the ultimate representative is, we're going to change it. We're going to go back. So if, let's say, 8 says 7 and 7 says 6 and 6 says 5 and 5 says, yep, it's me, I'm not going to leave it that way. I'm going to change it so that 6 still says 5, but 7 says 5 and 8 says 5. I'm going to, instead of having a path of length 3, 8 now has a path of length 1. 7 has a path of length 1. We're going to compress those paths so everybody knows the ultimate representative. So, to get the complexity for this is going to require an amortized analysis over the entire life cycle of the union find, and the result is kind of strange. So the result is the total complexity from going from n disjoint to one superset. The complexity is n times alpha of n. Alpha of n is a function. We're going to look at what it looks like in just a second. It's called the inverse Ackermann function. Now, you don't have to know this. You're not going to have to derive it. This is a thing for like 477. So I'm going to add a blank slide in here. And then, unfortunately, this is going to be really painful. PowerPoint has a bug in it where the resolution and the slide doesn't update properly. Okay, there we go. All right, so we've got the... You should be able to just see the slide now. Okay, so if we look at the Ackermann function, the Ackermann function looks like this. So the Ackermann function A grows very, very rapidly. Like A of 4 comma 5 is, I believe, greater than the number of particles in the known universe. So if that's true, then the inverse of that function, alpha, grows like this. It grows very, very slowly. If I ask, what's inverse Ackermann? What's inverse Ackermann of 1,000? It's like 2. What's inverse Ackermann of 1,000,000? Like 3. Inverse Ackermann of 1,000,000,000, 4. Inverse Ackermann of the number of particles in the universe, 4. So alpha is effectively less than 5. For any reasonable value of n, alpha of n is less than 5. So for any problem that we could solve, alpha never has a value bigger than 5. It's not like log. Like my example kind of sounded like log, but it's not. It's much slower even than log. So you'll never ever see an inverse Ackermann greater than 5, or even 5 would be unlikely. So what this is saying is basically this is approximately equal to O of n times 5 for the entire life cycle, to go from n disjoint sets up to one superset of everything is O of n times alpha of n, which means that basically the cost of each union, the cost of one union, is alpha of n, due to all of the things that we did. The I know someone who knows someone, the representative of the representative, due to the path compression. So you will, in this, you could start to get a stick, but it's very unlikely that the stick will grow very long before path compression sets in and everybody has a length of 1 all of a sudden. So we've got another example in here, which we can go through really quickly. So everybody starts out as their own representative. And then, I'm going to change colors here. Okay, so we join 2 and 4. We ask them. 2 says 2, 4 says 4. They can be union, so 4 changes its representative to be 2. 1 and 2. 1 says 1, 2 says 2. They can be union. The second one, 2 says my representative is 1. 5 and 7, 5 says, and also when we do this, we stop because when I ask 5, who's your representative, we stop when someone says me. So 5 says 5, 7 says 7. They're different. So 7 can change its representative to be 5. 5 and 6. 5 says 5, 6 says 6. 6 changes its representative to be 5. And if we're drawing this, let's see. So 2 says 1. 4 says 2, 6 says 5, 7 says 5. We're going to have to get some crossings in there. And that's all the ones we've done so far. Okay. So then we say 8 and 5. Can 8 and 5 join? Yes. So 8 says 8, 5 says 5. 5 changes its representative to be 8. The second one always changes. And now if I ask, can 4 and 7 be joined? Well, to do this, I have to do a find on 4, and I have to do a find on 7. So when I do a find on 4, 4 says 2, 2 says 1, 1 says, yes, it's me. So we know the ultimate representative, find of 4 says 1, but in doing that, we compress the path so that 4 points directly to 1. When we ask 7, who's your representative? 7 says 5, 5 says 8, 8 says, yes, it's me. So we know we've reached the ultimate representative, but we also compress this path to change 7's representative to be 8 also. So we have compressed the part of the path that we asked about. We never asked about 6, so 6 doesn't get compressed yet. But if in the future we did a find on 6, we would compress 6's path so that 6 pointed directly to 8. So that's how the path compression works. So union is alpha of n, find is alpha of n if we amortize it over the lifetime. So some of them will be O of 1, some of them will be a little bit longer than 4 or 5, but in the amortized analysis, because of the path compression, we will get an average cost that is constant. Okay, you can look over the study questions, and that's it for today. I'm going to get some more slides posted for the next couple days. I was interrupted doing that by the buffering problems, so apologize for those. Hopefully we'll get those resolved in the future so that we don't have too much competition for resources during lecture time. So thanks everyone, and we'll see you in office hours.